Hello guys, today we will deal with the differentiability of function of two variable. But before starting this topic, I just want to recall all of you what is the definition of the differentiability of function of in case of function of single variable. So as we know that suppose we have y is equal to fx, a function of one variable, and we want to find its differentiability at point x is equal to a. So we say the function y is equal to fx is differentiable at a point x is equal to a if the limit x s tends to 0 f a plus h minus f a upon h, this is equal to, this exists and equal to f of a, f dash a. We can also rewrite this equation as f a plus h minus f of a upon h in plus epsilon. Epsilon is because of this limit. Okay, because when limit s tends to 0, then epsilon tends to 0, and epsilon is here function of x only. Okay, so because epsilon is very small quantity, so here f a plus h minus f of a is equal to f dash a into h plus epsilon into h. Now in place of h, if we use del x, so we get f a plus del x minus f of a, this is equal to f dash a into del x plus epsilon del x, and after simplifying this we can write it equal to minus f of a minus f dash a into del x, and this is equal to epsilon into del x. So from here we can say that if this function, because this is function of, if del x we suppose this is h, then this becomes function of, it is g function of del x. If function of del x, that is this is equal to epsilon into del x. So we are calling this function as function of del x, and we give this name g function. If this tends to 0, as del x tends to 0, then we say the function fx, then we say the function fx is differentiable at point x is equal to a. So this is the another way in which we can say the given function is differentiable at a given point. So in the case of function of two variable, we will use this approach here. So suppose we have function of two variables z is equal to x comma y, and we want to find its differentiability at point a comma b. So first of all we will find here del z, then del z will be equal to fx at point a comma b into del x plus fy at point a comma b del y, and in place of epsilon we will use epsilon 1 del x plus epsilon 2 del y here. Now when del x comma del y tends to 0, epsilon 1 epsilon 2 also tends to 0, where epsilon 1 is function of del x del y, and similarly epsilon 2 is also function of del x comma del y. Okay guys, so first of all we will find this one, and here you can see this term fx into del x, fy into del y, we call it total derivative and we represent it by del dz. So from here, this equation we can rewrite this as this is equal to del z into dz plus fy at point a comma b dy, this is dz epsilon 1 into del x plus epsilon 2 into del y. So we can also rewrite this equation like this. Suppose this is equation. Now from a equation we can take dz left hand side and we get epsilon 1 into del x plus epsilon 2 into del y. Now taking del rho is equal to del x square plus del y square, we get, and dividing it by above equation we get del z minus dz whole upon del rho is equal to epsilon 1 into del x upon del rho plus epsilon 2 into del y upon del rho. Now taking limit when del x comma del y tend to 0, 0, 0, we observe that the del rho is also tends to 0. Taking limit del rho tends to 0 both sides in equation B, we call this equation number B. So what we get here, limit, this is equal to limit del rho tends to 0 del z dz upon del rho is equal to epsilon 1 into del x limit del rho tends to 0 upon del rho plus epsilon 2 limit again del rho tends to 0 del y upon del rho. We can observe that the del x upon del rho both are, and del y upon del rho both are the mod values less than 1, so that means both are the finite values. So if when del x comma del y, if function is differentiable, then dx dy tends to 0 and epsilon 1 epsilon 2 tends to 0, then the left hand side limit tends to 0. That means when epsilon 1 tends to 0 comma epsilon 2 tends to 0 as del rho tends to 0, then we say the limit del rho tends to 0 del z minus dz upon del rho also tends to 0, or we say fxy is different